Picture this. A spacecraft, hurtling through the void of space, is on a collision course with the moon. It's a lonely journey, the silence of space broken only by the hum of the craft's failing systems. The lunar surface looms larger and larger, a tapestry of gray craters and ancient dust. Then, impact. There's no fiery explosion, no earth-shattering boom. The moon has no atmosphere to carry sound or ignite fuel. The impact is a silent ballet of destruction, visible only as a sudden bloom of debris rising from the surface. This is a crash landing unlike any we've ever seen on Earth. The spacecraft, once a marvel of engineering, is instantly reduced to a shower of metal and wire. It leaves behind a fresh scar on the moon's face, a testament to the unforgiving nature of space and the raw power of uncontrolled descent. To understand a lunar crash, we need to talk about what's not there: air. Earth's atmosphere is like a protective blanket. It causes friction, generating heat that burns up small meteors before they reach the ground. It also slows down larger objects, giving us a fighting chance to prepare for impact. The moon has no such luxury. Its atmosphere is so thin it's practically non-existent. There's nothing to slow down incoming objects, no air resistance to speak of. A spacecraft approaching the moon will slam into its surface with its full velocity, the force of the impact magnified by the lack of atmospheric braking. This absence of atmosphere makes lunar landings a delicate dance. Spacecraft have to use thrusters to carefully control their descent, slowing down just enough to touch down gently. A miscalculation, a malfunctioning thruster, and a soft landing can quickly turn into a crater-forming event. Imagine a rock about the size of a basketball falling towards Earth. This rock, known as a meteor, embarks on a fiery journey as it plummets through the vast expanse of space towards our planet. It enters the atmosphere, friction ignites it, and it burns brightly, becoming a shooting star. This mesmerizing display is a result of the intense heat generated by the friction between the meteor and the atmospheric particles. Most likely, it burns up completely before hitting the ground. The majority of meteors disintegrate into tiny particles, never reaching the Earth's surface. If it's large enough, it might survive the fiery entry, but it will be significantly smaller and slower by the time it lands. These surviving fragments are known as meteorites, and they can provide valuable scientific insights. Now imagine that same rock falling towards the moon. The moon's environment presents a stark contrast to Earth. There's no atmosphere to slow it down, no friction to burn it up. The lack of an atmospheric shield means the meteor remains intact as it hurtles towards the lunar surface. It slams into the lunar surface with the force of a bomb, excavating a crater many times its size. The impact is so powerful that it sends shockwaves through the lunar crust. The impact energy is released in a spectacular display of flying debris and molten rock. This dramatic event leaves a permanent mark on the moon's surface. This difference in atmospheric braking explains why Earth's surface is relatively young compared to the moon's. Earth's dynamic atmosphere and geological processes continuously reshape its surface. Most impact craters on Earth have been eroded away by wind, water, and geological activity. These natural forces act as Earth's erasers, gradually wearing down the evidence of past impacts. The moon, on the other hand, wears its history on its sleeve, its ancient craters a testament to billions of years of cosmic bombardment. Without an atmosphere or active geology, these craters remain as enduring records of the moon's tumultuous past. When a spacecraft crashes into the moon, the impact energy is released in a fraction of a second. This sudden release of energy is akin to a small explosion, sending shockwaves through the lunar surface. This energy vaporizes the spacecraft itself and superheats the lunar surface at the point of impact, creating a superheated plasma. The intense heat and pressure transform the immediate area into a glowing, molten state. The plasma expands rapidly, pushing outward in all directions, excavating a bowl-shaped depression that we call a crater. This process happens in mere moments, but the resulting crater can last for millions of years. The size and shape of the crater depend on several factors: the speed and mass of the spacecraft, the angle of impact, and the composition of the lunar surface at the impact site. Faster impacts create larger craters, while the mass of the spacecraft determines the depth and width. A head-on collision will create a symmetrical crater, while a glancing blow will produce an elongated one. The angle of impact can dramatically alter the final appearance of the crater, making each one unique. In 2009, NASA's L-Cross mission deliberately crashed a spent rocket stage into a permanently shadowed crater near the moon's south pole. This mission was designed to search for water ice in these shadowed regions. The impact excavated tons of lunar material, including water ice, which was detected by a trailing spacecraft. This discovery was significant, as it confirmed the presence of water on the moon, a crucial resource for future lunar missions. This mission demonstrated that intentional lunar crashes can be valuable tools for scientific exploration. By studying the debris and materials ejected from these impacts, scientists can learn more about the moon's composition and history, paving the way for future exploration and potential colonization. Section 5. A tiny scar on a giant face. The moon's resilience. The moon has been bombarded by asteroids and comets for billions of years. Its surface is littered with craters of all shapes and sizes, evidence of its violent past. So, what's one more crater from a human-made spacecraft? In the grand scheme of things, the impact of a spacecraft is insignificant to the moon. It's like throwing a pebble into the Grand Canyon and expecting to see a difference. The moon is a massive celestial body, and even a large spacecraft is minuscule compared to its size and mass. While a spacecraft impact will create a new crater, it won't significantly alter the moon's overall structure or appearance. The moon will continue to orbit the Earth, its familiar face virtually unchanged by the addition of one more scar. Section 6. Secrets from the depths. Unlocking lunar mysteries. Crashing a spacecraft into the moon might seem destructive, but it can actually be a valuable tool for scientific discovery. This method, known as impact excavation, allows scientists to access materials that lie beneath the moon's surface. These materials have been untouched for billions of years, providing a pristine record of the moon's history. The impact excavates material from beneath the surface, material that has been shielded from the harsh solar radiation for billions of years. This untouched material can reveal secrets about the moon's geological past, including its volcanic activity and the presence of ancient water sources. By analyzing the composition of the ejected material, scientists can learn about the moon's internal structure, its formation, and its history. This analysis can provide insights into the processes that shaped not only the moon, but also other rocky bodies in our solar system. The L-Cross mission, for example, confirmed the presence of water ice in permanently shadowed craters at the lunar poles. This was a groundbreaking discovery, as it suggested that the moon could harbor resources essential for future human exploration. This discovery has significant implications for future lunar exploration, as water ice could be used as a resource for drinking water, oxygen, and even rocket fuel. The ability to utilize these resources could make long-term lunar missions more feasible and sustainable. Intentional lunar crashes could also help us search for signs of past life on the moon. By examining the ejected material, scientists can look for organic compounds or other indicators of past biological activity. While the lunar surface is considered sterile today, it's possible that microbial life existed on the moon billions of years ago when it was volcanically active and may have had a thicker atmosphere. Discovering evidence of past life on the moon would not only revolutionize our understanding of the moon, but also provide clues about the potential for life elsewhere in the solar system. Section 7. Oblivion, the spacecraft's final bow. The moment a spacecraft crashes into the moon, it ceases to exist as we know it. The immense energy released upon impact vaporizes the spacecraft, turning metal, plastic, and electronics into a superheated plasma. This plasma quickly cools and condenses, forming a... Section 8. To crash or not to crash. An ethical quandary. The idea of intentionally crashing spacecraft into the moon raises ethical questions. Some argue that we have a moral obligation to preserve the pristine nature of celestial bodies, even if they are seemingly barren like the moon. They argue that we should explore space responsibly, minimizing our impact on other worlds. Others argue that the potential scientific gains outweigh the ethical concerns. They point out that the moon has been bombarded by natural objects for billions of years, and a few more craters from human-made objects won't make a significant difference. They believe that we should use all the tools at our disposal to unlock the secrets of the universe, even if it means sacrificing a few spacecraft. Section 9. Weighing the risks and rewards, the future of lunar impacts. As we venture further into space and our technological capabilities increase, the debate over intentional lunar impacts is likely to continue. There's no easy answer, as it involves weighing the potential benefits of scientific discovery against our ethical responsibilities as explorers. One thing is certain, we need to proceed with caution and careful consideration. Before we crash another spacecraft into the moon, we need to fully understand the potential risks and rewards, and we need to have a clear scientific justification for doing so. The moon is a valuable resource for scientific exploration, and we need to treat it with respect even as we seek to unlock its secrets.